Okay, so this is Lecture 4, Part 3. In this lecture, we'll be talking about double angle, half angle, and product sum formulae of trigonometric functions. So I'll explain to you what those are all about. All right, so double angle formula. What we mean by that is this. Suppose I ask you what the sine of 2x is. So essentially what we're doing is we're doubling the argument of sine 2x. Well, it turns out that sine 2x can be written as x plus x, sine of x plus x, right? Because x plus x is 2x. All right, and then we just invoke the sign of a sum from the previous lecture. So this would be the sine of x times the cosine of x plus the sine of x times the cosine of x. Okay, and that's equal to 2 sine x cosine x, right? So that's the double angle formula for sine 2x. Not a bad idea if you memorize this. Okay, so we can do the same thing with the cosine of 2x. Same technique. Cosine of 2x is equal to cosine of x plus x, which is equal to, from the cosine of a sum of two numbers, we know is the cosine of x times the cosine of x minus the sine of x times the sine of x. Okay, which we know to be cosine squared x minus sine squared x. Okay, so there's one formula for the cosine of 2x, or the double angle formula for cosine 2x. Of course, we know that we recognize that that term could be replaced by its expression in terms of cosine x. We know that sine squared x from the Pythagorean identities is simply 1 minus cosine squared x. And when we simplify this, this would be 2 cosine squared x minus 1. Okay, so there's another expression. Or if you want to express cosine of 2x in terms of sine, we can take this formula and replace cosine squared x with its Pythagorean identity, which is 1 minus sine squared x minus sine squared x, which is equal to 1 minus 2 sine squared x. So all three formulas, there are three representations for the cosine of 2x. All right. So for example, suppose we have, if cosine x is equal to negative 2/3, and x is an element of the third quadrant, okay, find the cosine of 2x. Okay, and the sine of 2x. Okay, so how do we do that? Well, the cosine of 2x is equal to, I suppose we could use this formula, one of the three mentioned previously, 2 cosine squared x minus 1, okay, and then we just plug in negative 2/3 for cosine x, so this would be 2 times negative 2/3 quantity squared minus 1, which is equal to 8/9 minus 1, which is equal to minus 1/9. Okay, and so the sine of 2x then is equal to 2 sine x cosine x. Okay, and so we know that the sine of x from the Pythagorean identity is equal to plus or minus the square root of Sorry about that. The video drivers on this machine aren't the best. Okay, so that's the sine of 2x. Okay, so we know that the sine of x is equal to plus or minus square root of 1 minus cosine squared x. All right, so we have that result. Since we're in quadrant 3, well, is it quadrant 3 yeah. Since we're in quadrant 3, the sine x is negative in quadrant 3, so we'll have to resort to using the negative value. So in quadrant 3, sine x is equal to negative of 1 minus cosine squared x. Okay, and so we know that the cosine of x is negative 2/3. So in quadrant 3, the sine x must be the negative or the square root of 1 minus, what is that, 4/9 would be cosine squared. And so that would be the negative of the square root of 5 over 3. Okay, so therefore the sine of 2x then is 2 times negative 5 over the square root of 3 times the cosine of x, which is negative 2/3. So the result is, what is that, 4 times the square root of 5 over 9. Okay, so result. All right. So now let's do this. Another example. Let's prove sine 3x over sine x cosine x is equal to 4 cosine x minus secant x. Okay, so it'll probably be a lot easier if we work on the left-hand side, because we can reformulate sine 3x as sine x plus 2x. And then if we multiply upstairs and downstairs, we can reformulate the denominator as 2 sine x cosine x. Okay, which we know to be sine of 2x. So this would be 2 sine x plus 2x over sine of 2x. Okay, so continuing forward, we can use the sign of a sum. So this would be 2 times sine x cosine 2x plus sine 2x cosine x, all over sine 2x. Okay, and so if we split the fractions, we would have 2 sine x cosine 2x over sine 2x plus cosine x, plus that would make that 2 cosine x, right? Because the sine 2x's would cancel, so that's 2 cosine x. All right, so let's see here. What can we do with this? Well, we know that, I guess we'll have to expand this back out. So we'll have 2 sine x cosine 2x over 2 sine x cosine x plus 2 cosine x, and the 2 sine x's will cancel. So cancel, cancel. All right, and I guess we could go ahead and recast cosine 2x. Say probably a good choice would be to replace cosine 2x with its expression in cosine x. So this becomes, say, 2 cosine squared x minus 1 over cosine x, okay, plus 2 cosine x, okay, and so that would equal to splitting this term right here into 2 fractions. Doing the division, we'll have 2 cosine x minus 1 over cosine x, okay, plus 2 cosine x. All right, and so that would equal to what we're targeting. That's 4 cosine x minus secant x, which is what we want. See, that's what we wanted right here. Okay, so yeah, so that's how one way of doing it. I introduced a redundant step, but it's okay. That can happen. All right. Okay, so let's talk about half-angle formulae. So we did double angle formulae, so half-angle formulae. So what's that all about? So next page. Okay, so for instance, we know that from the previous work, we discovered that the cosine of 2x was equal to 1, or rather 2 sine squared x. Let's see, 2 sine squared x. Yeah, 1 minus, let's see here, 2 sine squared x minus 1. Yeah, 1 minus 2 sine squared x. Okay, so that originated from the double angle formula. Let me check. Yes. Okay, so now what would happen if we solve for sine squared x? Okay, so sine squared x so sine squared x then is equal to 1 plus cosine 2x. Man, what is going on with this video driver? 1 plus cosine 2, excuse me, 1 plus cosine 2x. That should be 1 minus cosine 2x, sorry. I'm having trouble with my video driver here on this. One minus cosine 2x over 2. Okay, so let's keep this result around. And then we also know that, so we'll use this in just a minute. Okay, so we also can say that cosine squared x is equal to 1 plus cosine 2x over 2. Right, so we'll use that result. Now, the tangent squared of x then is equal to sine squared x over cosine squared x, which is equal to 1 minus cosine 2x over 1 plus cosine 2x. Okay, and we'll use that in just momentarily as well. So, so the question is, we want to express sine squared x cosine squared x. Well, I'll write it down. So let's express sine squared x cosine squared x in terms of the first power of cosine. Okay. So we don't want any square terms. All right, so we just plug in those relations we just derived. So sine squared x cosine squared x, okay, is equal to 1 minus cosine 2x over 2 times 1 plus cosine 2x over 2, and we can simplify that. So doing the multiplication, we have a plus b times a minus b, and of course that yields 1 minus cosine squared 2x over 4, right? And so that's 1/4 minus cosine squared 2x over 4. Okay, so we can replace cosine squared 2x now. Okay, so we know that the cosine squared of x is this. So if we replace x with 2x, then this term will become 4x, right? Because of what? Composition. Okay, so this becomes 1/4 minus 1/4 times 1 plus cosine of 2 times 2x, okay, over 2, which is equal to 1/4 minus 1/8 minus cosine 4x over 8. Okay, and then so simplifying further, 1/4 minus 1/8 is 1/8. So this would equal to 1/8 minus cosine 4x over 8. Okay, so what we did here was we replaced this expression, sine squared x cosine squared x, in terms of the first power of the cosine. See, the cosine function is only to the first power. Okay, and we use composition to achieve the result. All right, so now the half angle formulas. Okay, so let's prove, next page. So we want to prove something like a half angle formula for this. Well, I'll give you the half angle formulas and then we'll derive them. Okay, so for instance, the sine of x over 2. Okay, it turns out that that's equal to plus or minus the square root of 1 minus cosine x all over 2. And that's all, this rational function is under the radical. And the cosine of x over 2 is equal to 1 plus the cosine of x all over 2. And that should be plus or minus. Okay, plus or minus. That's a plus or minus. Okay, so let's prove this one. So we know that the sine squared of x is equal to 1 minus cosine 2x over 2. Okay. And let's see here. So the sine squared of x over 2. I'm sorry, that should be the sine squared of x over 2. The sine squared of x over 2. Okay, we just replace x with x over 2. That would be 1 minus cosine x over 2. Okay, and then we take the square root of both sides, so that implies that the sine of x over 2 is equal to plus or minus the square root of 1 minus cosine x over 2. Okay, and so the sign, plus or minus, the sign that is, plus or minus depends. Okay, so the choice of plus or minus depends on which quadrant. X over 2 is in. Okay, all right. So the cosine of x over 2 is proved similarly, and I'll leave that to you as an exercise, right? So how about we compute the half angle formula of the tangent of u over 2. Okay. So the tangent, not u over 2, but x over 2, the half angle formula for the tangent function would just simply be the ratio of the half angle of sine over the half angle of cosine. So that would be plus or minus the square root of 1 minus cosine x over 1 plus cosine x. Okay, and what we can do then is we can rationalize this. So that would equal to plus or minus. Man, I'm having trouble with my video here. Sorry, that's not a cancellation. It's a problem with the computer. 1 minus cosine x over 1 plus cosine x. Okay. All right. So now, what we do is we rationalize the numerator to get a different result. So we have 1 minus cosine x over 1 plus cosine x times 1 minus cosine x over 1 minus cosine x. So that's the rationalization, and then that would equal to plus or minus the square root of, okay, so that would be 1 minus cosine x quantity squared divided by 1 minus cosine squared x. Okay, and so that's just equal to plus or minus what? 1 minus cosine x quantity squared divided by sine squared x. Now, when we take the square root of a square, that becomes the absolute value. So that just becomes plus or minus the absolute value of 1 minus cosine x over sine x. Okay, so we have that result. Okay. Okay, so we know that the tangent of, turns out that the tangent of x over 2, the sine, the secant that is, the sine of the tangent of x over 2 has the same sine as the sine of x. Right? So we can say that, so that aids us in simplifying the plus minus. So if sine is plus, okay, then the tangent of x over 2 is just simply equal to 1 minus cosine x over sine x. Okay, and let's see what else. Okay, right. Okay, and I'll leave it to you as an exercise. Okay. Oh, also, if sine x is negative, okay, if the sine x is negative, then the result still holds as well. Okay, so this is the half-angle formula for the tangent of x over 2 right here. Remember, if sine x is negative, then we replace the absolute value of sine x with the negative of sine x, and so the tangent function will be the same as the sine x, so it'll be negative as well. Okay. All right. So there's the half-angle formula for the tangent function. Okay, and I'll leave it to you to show that this also holds. And this is probably found by rationalizing the denominator. We found the blue result by rationalizing the numerator, but if you rationalize the denominator, you probably get something that looks like this. Okay, so this is an alternative form. Okay, so we can do some examples. Say, how about the sine of 22.5 degrees? Without a calculator, let's calculate. Well, that just is simply the sine of 45 degrees over 2, which we used a half-angle formula for the sine function, so that would be the square root of 1 minus cosine 45 degrees over 2, okay, and so that is equal to 1 minus the square root of 2 over 2 over 2, and so this is just equal to, multiplying upstairs and downstairs by 2, this is just equal to 1/2 times 2 minus the square root of 2. Okay, so there might be a web assigned question like that. Okay. Find the tangent of u over 2. If sine of u is equal to 2/5 and u is in quadrant 2. Okay, this symbol right here means and u is an element of quadrant 2. So we know that the cosine of u is equal to negative of the square root of 1 minus sine squared u in quadrant 2. Okay, and so that's equal to negative of the square root of 1 minus 4/25, which is equal to negative the square root of 21 over 5. Okay, so that leaves the tangent of u over 2 equaling to 1 minus the cosine of u over the sine of u. Okay, and so that would be 1 plus the square root of 21 over 5 divided by 2/5. Okay, and so that's equal to 5 plus the square root of 21 over 2. All right. Okay, so that's how that works. So now let's talk about the product to sum formulae. Okay, product to sum formulae. Product to sum. And I don't know if I'm going to prove these. I think the proofs are somewhat obvious. I think it would be worth your time to at least do 1 or 2 of them, or perhaps more. But anyway, I think the derivations will be obvious once you see the formulas. So for instance, suppose I have a product of sine of u times the cosine of v. And we want to convert this product into a sum. Okay? So it turns out that this sum is equal to 1/2 times the sine of the sum of u and v plus the sine of the difference of u and v. And of course, the way you can prove that is just do the expansion. Calculate the sine of u plus v, calculate the sine of u minus v, add them together, multiply them by 1/2, and you should get the result. So I think the proof you can handle yourself. Might be a web assigned question. Okay, so the cosine of u times the sine of v is equal to 1/2 times the sine of the sum of u and v minus the sine of u minus v. Okay. Okay, and so again, I'll leave that to you to prove. Okay, note that these two products are not the same. Okay, then we have the cosine of u times the cosine of v. Okay, so that would be 1/2 times the cosine of u plus v plus the cosine of u minus v. Okay, and then the fourth one, of course, would be the sine of u times the sine of v. That's the sine of u times the sine of v, and that would equal to 1/2 times the cosine of the difference of u and v minus the cosine of the sum of u and v. Okay, so now with these formula, I'm going to use them and use them to solve problems. The next example. So suppose we want to express this product, the sine of 3x times the cosine of 5x as a sum. Okay? So what we could do is we could let u equal to 3x, and we could let v equal to 5x. And so what we want to do is we want to write sine of u times the cosine of v as a sum. And so we recall that that's the sine of u times the cosine of v is 1/2 times sine of u plus v plus the sine of u minus v. Okay, and so wiring in the values, that would be 1/2 times the sine of u plus v, which is 8x. Okay. Oh, I'm sorry, that's the wrong formula. No, wait. Sine of cosine of v. Sine of u times the cosine of v. Okay, yeah, we can keep going on with this. Okay, so that would be 1/2 times the sine of 8x plus the sine of u minus v, which is negative 2x. Okay, and then of course that's just equal to 1/2 times the sine of 8x minus the sine of 2x. Okay, so we have that result. Okay, yeah, so seems pretty straightforward. Now next topic we'll do sum to product formulae. Okay, so if we have the sum, can we convert it into a product? So sum to product formulae. All right, so if we let u equal to x plus y over 2, and we'll let v equal to x minus y over 2. So the sine of x plus y over 2 times the cosine of x plus y over 2. Okay, so we have a product that would equal to 1/2 times the sine of the sum. I'm sorry, let's make that the cosine of x minus y. Okay. So that would be 1/2 the sum of u plus v, which is x, plus the sine of the difference, which is y. So u minus v is y. Okay, so that's how we can convert sum to products. And so sine x, so we have sine x plus sine y, of course, is 2 times this quantity on the left. Okay, so proceeding further, we have 4 relations we can identify. So I would expect you to be able to prove these. So we have the first one, which we just proved, the sine x plus sine y is equal to 2 times the sine of x plus y over 2 times the cosine of x minus y over 2. Okay, so we just proved that one. So these I would suggest you attempt on your own. So for instance, the sine of x minus the sine of y. Okay, to convert that into a product, it would be 2 times the cosine of x plus y over 2 times the sine of x plus y over 2. So you can prove this in the same fashion you would a trigonometric identity. All right, and then we have the cosine of a sum. Cosine x plus the sum of two cosines, that is, the sum of two cosines can be expressed as 2 times the cosine of x plus y over 2 times the cosine of x minus y over 2. And then we have the difference of two cosines can be expressed as 2, that's negative 2, times the sine of x plus y over 2 times the sine of x minus y. Now you can use your product formulas, product to sum formulas, to prove these identities, okay? Or you can do it the way we did here, which is what they did. The proof will involve using product to sum formulas from the previous note. Okay, so we can do an example. So let's prove, or let's convert the sine of a sum, or not the sine of a sum, but the sum of two sine functions, the sum of two sine functions, sine 7x plus sine 3x, into a product. Okay, so if we use the preceding formulae, that would equal to 2 times the sine of the sum of the two numbers. So that would be 7x plus 3x over 2 times the cosine of the difference. So that would be 7x minus 3x over 2. So simplifying, that would be 2 times the sine of 5x times the cosine of 2x. Okay. Now, WebAssign will of course have problems that will require to use each of the formulae of the sum of cosines, the sum of sines, and so forth. Okay, so be prepared for that. Okay, so let's prove a trigonometric identity. Next page. So let's prove this formula. This is an interesting formula. It has a lot of utility in engineering applications. The sine of 3x minus the sine of x divided by the cosine of 3x plus the cosine of x. Okay, we want to prove that that is equal to the tangent of x. Okay, so to do so, we can convert the sums and differences in the rational function into their product forms. Okay, so the numerator becomes 2 times the cosine of 3x plus x over 2 times the sine of 3x minus x over 2, and the denominator becomes what? 2 times the cosine of 3x plus x over 2 times the cosine of 3x minus x over 2. Okay, and so after simplifying, that would be 2 cosine 2x sine x divided by 2 cosine 2x times the cosine of x. You can see we have a lot of cancellations now. 2's cancel, cosine 2x is cancel. And so that equals the result we need. So that's equal to tan x. All right, so that will conclude section 4.3. Okay, so this will be lecture 4, part 4. In this topic, we're going to discuss what we mean by the inverse of the trigonometric function. So consider the sine function. This right here is shown here. So as you can see, I've got a sketch of what, 2 periods of the sine function. And obviously, the issue is that the sine function per se is not a one-to-one function. So the green piece, the green part of the function, or to make it all green. Okay, so just considering the entire 2 periods of the sine function, you can see it's not one-to-one. And so technically speaking, there's no inverse of this green curve because we have a many-to-one relationship. And so it's not one-to-one, and so the only way you can get an inverse of a function is if the function is one-to-one. So what we do is we take a modification. We take a portion of the sine function, which is shown in orange here. And why did I take this particular portion of the sine function? Well, for instance, this orange graph, this orange segment that you see here, flows through the full range of the sine function from -1 to 1. It also includes the origin, and of course the orange piece is 1-to-1. And so this, we identify this particular graph. I take the orange piece and I paste it right here, and now it's shown in blue. And we call this the principal part of the sine function, or principal sine x, principal sine. And you can see that, well, maybe so, maybe not so much, but the principal sine function is written using an uppercase S. Okay, and so this is the piece that we take the inverse of. When we talk about the inverse of the sine, we're talking about this graph and this graph alone. And this is what, when you type the inverse sine on your calculator, this is what you're doing. You're calculating the output for some value of x. And your calculator considers this curve as well to be the inverse sine function. So let's see here. So this is the principal sine part, and of course now that it's 1-to-1, we can flip the domain in the range of this blue curve to get the inverse of the blue curve, and so it's going to look something like this. Bear with me while I paste, extract a picture of it. So 1 second. So you understand what we mean by principal sine. It's that part of the sine function for which we can take the inverse of because it's 1-to-1. So let me copy something and paste it into the next slide. So again, the blue curve is the principal sine function, and the orange curve now is the inverse of the principal sine. Okay, and it's written as sine inverse of x. So as you can see, we flip the domain and the range. So the domain of the principal sine becomes the range of the inverse sine, and the range of the principal sine becomes the domain of the inverse sine function. So as stated here. And we write the inverse sine function, we can use lowercase. We write it as sine. This is not to be interpreted as a -1, it's to be interpreted as an inverse. Here's the domain, here's the range, and then the composition of the principal sine with its inverse is equal to x, of course, for x between -1 and 1, and the composition of the inverse sine with the sine, principal sine, is equal to x for x between -pi12 and pi12. Okay, so let's see here. So note these 2 statements here. Okay. The inverse sine of 1/2, of course, you can read from the graph, is pi4. Looks about like pi4, or maybe it would probably be pi3. I would say it's probably more closer to pi3. And the inverse sine of -1/2 is -π3, and the inverse sine of 3/2, of course, is not defined because 3/2 is not in the domain of the function. All right, so that's the inverse sine, what we mean by inverse sine. So we can solve a problem here. Something may crop up and we'll decide, so let me pull up a note. So let's calculate the cosine of the sine inverse of 3/5. I believe this will be part of the problem specification as well. Theta is between -π/2 and π/2. All right, so if the way it turns out that if we have something like this, the inverse sine of 3/5, that means that the sine of theta must equal to 3/5. Okay, and theta, of course, is constrained between -π/2 and π/2. So remember, the sine of theta is the opposite divided by the hypotenuse, as shown in this right triangle formulation. So that means this leg right here, using the Pythagorean theorem, calculates to be 4. So the cosine of theta then becomes 4/5, right? And then the tangent of theta becomes 3/4, and the cosecant of theta, which is just 1 over the sine of theta, is 5/3. So this restriction on theta right here allows us to use a triangle that's drawn this way. Basically, essentially a theta that's in the, say, first quadrant. Okay. All right. So let's talk now about the inverse cosine function. And conceptually, it'll be done similar as with the inverse sine function. We just need to select that principal part. So let me select out what we consider the principal cosine piece. Right, so inverse cosine. So for inverse cosine, we have, okay, so the blue curve is essentially 2 periods of the cosine function again. And obviously, again, the cosine function is a many to 1, so we can't take the inverse of the cosine per se, but what we can do is we can identify the principal part, which is shown in orange. Okay, so I'll take the orange piece out and I plot it on its own coordinate axes. So the inverse cosine function is the function cosine inverse with domain. Okay, so now in this case the domain ranges from -1 to 1, so it ranges to the full range of the cosine function. But this time the range is from 0 to pi. Okay, 0 to pi. And so we define inverse cosine of x equals to y, or the cosine y is equal to x. So the graph which is shown in green can also be said that the graph shown in green is the principal cosine, written uppercase C, of x. Okay, and then the domain of principal cosine x is from 0 to pi, and then the range is from -1 to 1. All right, so that's the principal cosine part. This is the part for which we take the inverse of the cosine. Okay, and so that's going to look something like this. Let me pull up a graph of it. So again, as you know, we just take the principal cosine function and swap its domain and range, and we'll get a graph that looks like this for the inverse cosine. Okay, like this. Okay, so swapping its domain and range. So this would be a graph of the cosine. So the whereas before the domain for principal cosine was 0 to pi, that now becomes the range, 0 to pi. And whereas before the range of the principal cosine was -1 to 1, well, that now becomes the domain. Okay, so there's the graph of the inverse cosine. All right, so we can do a problem involving inverse cosine. So let's see what we can do with that. Okay, so let's look at this problem right here. We want to calculate the sine of the inverse of cosine x and the tangent of the inverse cosine of x as algebraic expressions in x for x between -1 and 1. Okay, so the way we can do that is, let's see here, the sine of the inverse cosine of x. Okay, so we know we can start off by saying this. If we let y, well, not y, but how about theta? How about if we let theta equal to the inverse cosine of x? Then if we take the principal cosine of both sides of the equation, we'll have cosine theta is equal to x. And we know that cosine theta is equal to adjacent over opposite, over hypotenuse, excuse me, hypotenuse, okay? So that means adjacent over hypotenuse must equal to x, so that forces the hypotenuse to be 1. Well, and then we use the Pythagorean theorem to compute the length of the opposite side of theta, which turns out to be the square root of 1 minus x squared. So we complete the right triangle, okay? And then, so cosine inverse of x is merely theta. So we just calculate the sine of theta, which is opposite over hypotenuse, and we get this result. And obviously we have to have x between -1 and 1 because that's the domain of this function right here. And then of course the tangent of cosine inverse of x, well, the cosine of inverse of x we said is theta right here. So the tangent of theta is opposite over adjacent. And so you have this function, and then of course x can't be 0. And then how about the sine of 2 cosine inverse of x? Well, since cosine inverse of x is just theta, we can use the double angle formula to replace sine of 2 theta with 2 sine theta cosine theta. And then we plug in the value for sine theta, plug in the value for cosine theta, and we get this result. Okay, so an interesting exercise. Of course, there will be numerous web-assigned problems dealing with this. All right, so let's talk about the inverse tangent function and the inverse cotangent function. Okay, we'll talk about the inverse tangent function first. All right, so let me pull up the graph. Of the inverse tan function. And what do we mean by inverse tan function? Okay. So let's just talk, we're going to talk about inverse tan first, and then we'll talk about inverse cotangent. So shown here is the graph of the tangent function. And then, of course, when we talk about the inverse, we need to extract out the principal part. And so we'll just take the middle branch of the tangent function to be the principal part. So this part right here, this branch right here of the tangent function, we'll identify as the principal tan. And that's written as uppercase T. Okay, so this is the part for which we take the inverse tan of, because it's 1-to-1, and it cycles through the range of the tangent function. So so let's see, that's the principal tan, and so the inverse tan is shown in this graph right here. If we flip the domain and range, the domain here is from -pi-halves to pi-halves, so the vertical asymptotes will translate to horizontal asymptotes in the inverse, and since the function goes toward infinity, the output goes toward infinity as x approaches pi-halves, well then the output will go toward pi-halves as x approaches infinity. So the inverse tan function is a continuous function, its domain is the entire x-axis, and its range is from negative pi halves to pi halves. This open interval, it's an open interval, okay? Open interval. It does not include the endpoints. Okay, so inverse tan x is the number in the interval whose tangent is x. All right, so that's the inverse tan x. The inverse cotangent x follows similarly. Okay, so let's pull up the graph of that. Okay, so the same type of analysis will go on. It's not the same as the inverse tan, of course. So again, we'll need to identify the principal part of the cotangent function, and then flip the domain and range of the principal part to get the inverse cotangent function. All right, so here is the, okay, so here is y equals cotangent x. Sketched here. And so we'll take as the principal part this branch right here between 0 and pi. So this would be uppercase C. Okay, that's the principal part. And then if we flip the domain and range, okay, we'll get the inverse cotangent function, which is sketched here. All right. And it's a continuous function. The domain of the inverse cotangent function is the entire x-axis, and it has horizontal asymptotes. The x-axis is a horizontal asymptote, and the y equals to pi is a horizontal asymptote. This is pi right here. Pi is a horizontal asymptote. All right, so now let's talk about the inverse secant function. So let's explore what it is, its graph. Okay, so let me pull up the note. One second while I extract out the graph. Okay. So here, shown in green, is the secant function. Okay, and you know, as we explained in class, to graph the secant function, you start off by graphing the cosine function, which is shown in purple, and then you let the zeros of the cosine function be the vertical asymptotes, and then the local mins and local maxes of the cosine function be the vertices for the branches of the secant function. So it remains to identify the principal part of the secant function. And so one choice, it's not a unique choice, but I guess for this class we'll just let this one roll for the inverse secant, would be to choose what's shown in orange. Okay, so we'll consider the principal parts of the secant function to be this branch right here and this branch right here. Okay, so those are the principal parts. So, and that's written, of course, in uppercase. So that's the principal part of the secant function. And so we just reverse the domain and the range. So in this case, let's talk about this branch right here. So this branch, its domain is from 0 to pi halves. So that would map for its range right here. Okay, and then it's so the range from 0 to pi halves maps to the domain, and then the domain, I'm sorry, the range here maps from 1 to infinity. So we would have to map the domain from 1 to infinity, and then the vertical asymptote becomes a horizontal asymptote. Okay, and then we would do the same for this branch right here, the lower branch. So for the lower branch in the principal secant function, the domain is from pi to 3 pi over 2, so that becomes right here the range for the inverse part. And let's see, the vertical asymptote 3 pi over 2 becomes a horizontal asymptote, as shown here. And then the range of this orange piece from -1 to -infinity becomes the domain. Okay, so that's how we flip it. And so this rather peculiar looking graph would be the graph of the inverse secant function. Okay, and then of course the inverse cosecant function would be done very similarly. So let me pull up its graph. We have to identify the principal part. Okay, and so shown here is the graph of the cosecant function. So this is y is equal to cosecant x. Okay, not one-to-one as it stands, but as you know, the cosecant x is drawn with the sine function as a reference. Okay, so we need to pick off the principal parts of the cosecant function to get y equals principal cosecant x, and we'll say we'll go with these green branches right here, shown in green. So this is the principal part, and because it is one-to-one, right? And so to sketch its graph, again, the upper branch right here is asymptotic with the y-axis, so that would make it asymptotic with the x-axis for the inverse. The range is from 1 to infinity. So at 1, okay, so at the point pi halves, we have an output of 1. So at the point 1, we would have an output of pi halves, flipping those. And then as we go toward 0 in this direction, the output goes toward infinity. So in essence, 0 maps to infinity, so infinity must map to 0 for this. And so that's shown here. So that upper branch matches here, maps to here. And then we have the lower branch right here. So 3 pi over 2 has an output of -1 for the principal part, so -1 must have an output of 3 pi over 2. We flip those. Pi becomes a horizontal asymptote as shown here, and as x approaches pi, the output goes toward -infinity. So you'll have this particular branch. So we'll use this as the principal, or as the inverse of the cosecant function. Now bear in mind, we didn't have to go with these parts. We could have actually used this part. Okay, this would have worked just as well as the principal part. And I think there's a WebAssign question which asks you to sketch the graph of the inverse cosecant function where we consider this to be the principal part. Okay, so it's the same exercise. All right, so there you have it. Those are the inverse trigonometric functions. Okay, so that will conclude Lecture 4, Part 4.